Okay, the last L'Hopital form, or should I say the last forms. 0 to the power of 0. We've learned that 0 to any power is 0, and we've also learned that anything to the power of 0 is 1. So 0 to the power of 0 is an indeterminate form. Another indeterminate form would be infinity to the power of 0. And then the last one, which I think is the most fun, is 1 to the infinity. So let's talk about that for a second. In a bubble, if I said 1 to the power of infinity, that would be 1 times 1 times 1 times dot dot dot, and that would clearly equal 1. So I'm not suggesting that if you take 1 and multiply it by 1 an infinite many times, it's something other than 1. But this indeterminate form is important if you have a, let's say, a base that's approaching 1, and then simultaneously its exponent is approaching infinity, something like this. If I took the limit as x approaches infinity of 1 plus 1 over x to the x. This is actually going to be example 2, but I want to talk about it here for just one moment. See, this base is not equal to 1. It's going to be eventually approaching 1. See, this expression here will eventually approach 0, so the base will eventually approach 1. And then at the same time, the exponent will be approaching infinity. So it's not truly 1 to the power of infinity. It's an indeterminate form where it's approaching 1 and then the base is approaching infinity. So let's take a look at some examples. In all these examples, in all these forms, the technique is the same. Example 8. This is the classic example. So I look and I see that I'll have the indeterminate form 0 to the power of 0. Now I'm going to ask that you do a couple things precisely the way that I do them here so that you get comfortable with the logic. I'm going to start off by saying let y equal the expression we're finding the limit of, x to the power of x. And if I let that be the case, then essentially what I'm trying to find here is the limit as x approaches 0 from the right of y. So I've just made this expression equal to y so that it works out nicely in the end. Okay, so the next step is after letting y equal x to the power of x, I'm going to take the natural log of both sides. So the natural log of y then becomes x times the natural log of x using properties of logs. So I'm not directly finding the limit that I desire. First, I'm going to find the limit as x approaches 0 from the right of the natural log of y. It's not the real limit I want. The real limit I want is here. This is a temporary step. So the limit as x approaches 0 from the right of the natural log of y is equal to the limit as x approaches 0 from the right of x times natural log of x. So I'm going to do this limit. In order to do this limit, I have to use L'Hopital's rule. So you see here, this is going to be 0 times infinity, or 0 times negative infinity. So that says, according to L'Hopital, maybe stop here, press pause, work out this limit as I now work it out. So this is going to be the limit as x approaches 0 from the right. If you recall, we want to keep natural log on the top, and on the bottom we want to write it as the reciprocal. So this is going to give me the indeterminate form of infinity over infinity. So I'm ready to do the standard derivatives under L'Hopital's rule. 0 from the right, the derivative of the top is 1 over x, and the derivative of the bottom is negative 1 over x squared. If I can simplify, then I must simplify, and so I shall. This is the limit as x goes to 0 of, if I multiply reciprocal, I see that this is just going to give me the expression of negative x. and as that goes to 0 from the right, equals 0. I'm going to put a box around this, but this is not my final answer, and that's a mistake that many people make doing this form. They get to this answer and they are joyful. Yay, joyful, but this is not the limit that I ultimately desire. That 0 represents the limit as x goes to 0 from the right of the natural log of y. So can you guess what the answer to the original is going to be? Now, if you are thinking to yourself, the answer is simply e to the 0, which then equals 1, then you are absolutely correct. But I'm going to ask, please, that you be a technician about this. So the limit as x approaches 0 from the right of y is equal to the limit as x approaches 0 from the right. Now watch what I do. I'm going to say e to the natural log of y. See, e and natural log are inverses of each other, so I can make that statement. And so now, if I employ rules of limits, then the limit actually applies to the portion that changes. E is a constant, so this is the limit of y, and then it's e, and we found this limit here already to equal 0, so my final answer is 1. After you do this a couple times, you'll be satisfied with the logic. And some people ask the question, do I have to write all this? And the answer is yes. I'm not permitting you to just simply write the answer. You will receive partial credit, but to receive full credit, I would like you to write out the full statement. Example 9, the limit as x goes to infinity of base 1 plus 1 over x, all that to the power of x. Now some of you might know the answer to this automatically. You might know that the answer is e. And I'll talk more about how this applies in real-world context in just a moment. But what we're going to do now is we're going to prove that the answer to this limit is e. Alright, so we see that we have the indeterminate form here, 1 to infinity, as I described in the introduction to this section. Okay, so first step, let y equal 1 plus 1 over x to the power of x. And we want to find the limit as x approaches infinity of y. Next, take the natural log of both sides. So the natural log of y equals x times the natural log of 1 plus 1 over x. Next, find the limit as x approaches infinity of the natural log of y, which is the limit as x approaches infinity of x times natural log of 1 plus 1 over x. Perhaps you want to pause here, or perhaps you've already worked it out. Alright, so this gives us the indeterminate form. Well, if I plug infinity in for x, it's infinity. Now this one's fun. If I plug infinity in for x, then it's 1 plus 0, and the natural log of 1 plus 0, the natural log of 1 is 0. So that's the indeterminate form. Alright, we're ready to use standard L'Hopital. Actually, no, I'm not. I have to manipulate this. I'm going to write it natural log function on top and a reciprocal function on bottom. Now I'm ready to do standard L'Hopital derivatives. Okay, let's not forget how to do a derivative. So the derivative of the top is 1 over 1 plus 1 over x, but then I have to take the derivative of the stuff, which is going to give me negative 1 over x squared. Now I'm going to do the derivative of the bottom, and that gives me negative 1 over x squared. If I can simplify, then I must simplify, and so we shall. This is kind of nice as this cancels out, leaving us with 1 over 1 plus 1 over x. Now when I plug infinity, this value here is going to 0, and the whole thing is going to 1 over 1, or simply 1. That is not the end, my friends. We want the limit as x goes to infinity of y, which is the limit as x goes to infinity of e to the natural log y, which equals the limit as x goes to infinity of, well, let's see here. Actually, e to the limit as x goes to infinity natural log y. I found this limit earlier, so it's e to the 1, or simply e. Yay, we proved it. Alright, let's move on to the next example. I want you to memorize the one we just did. In fact, I'm going to write it again. The limit as x goes to infinity, 1 plus 1 over x to the x. If you see this exact one on the exam, please tell me you know the answer is e, and you don't have to show any work. So that's going to lead to the next example, number 10. And in this example, suppose I have the limit as x goes to infinity of 1 plus 1 over x to the 5x. Can you tell me what that's going to equal without going through all the work? Think about it. Did you say e to the power of 5? If you did, you're correct. And that's what I want you to be able to do on the exam also. But I also want you to be a little bit more detailed. So what we're going to do is say the limit as x goes to infinity of 1 plus 1 over x to the x to the power of 5. See, power to a power we multiply. So then this is really written as the limit as x goes to infinity, 1 plus 1 over x to the x, and then that limit is taken to the power of 5. If we've memorized this, this goes to e, and then it's e to the power of 5. That's what I'd like you to show me on the test, in the event that I give you one like that. Last example, number 11. Limit as x goes to 0 from the right, base x plus cosine 2x, exponent cosecant of 3x. I would ask you in a moment to press pause and work this out yourself. This one is not as hard as it seems. It will be the indeterminate form, 1 to infinity. And once you do L'Hopital's rule once, you don't have to simplify. You can directly substitute. So work this one out and then follow the video to make sure you've done it correctly. Okay, so we said, or I said, this is the indeterminate form 1 to infinity. So I'm going to use my standard let y equals x plus the cosine of 2x to the power of cosecant of 3x. I want to find the limit as x goes to 0 from the right of y. When I've done that, I've finished the problem. So first, natural log of y equals the cosecant of 3x times natural log x plus the cosine of 2x. And the limit as x goes to 0 from the right of natural log y equals the limit as x goes to 0 from the right, cosecant 3x times natural log x plus cosine 2x. This gives me infinity times 0, so I have to rewrite it. Limit as x goes to 0 from the right, and I'll leave the natural log on the top, and on the bottom it'll be 1 over cosecant, or simply the sine of 3x. Now we're at standard L'Hopital. If I plug these in, I'm going to get 0 over 0. So I have the limit as x approaches 0 from the right. All right, get ready for the derivative. So this is going to be 1 over x plus the cosine 2x times the derivative of stuff, which is going to be 1 minus 2 sine 2x. All of that was the derivative of the numerator. Now the derivative of the denominator is 3 cosine 3x. Now here's what I was saying before. We actually don't have to simplify. We are permitted to plug 0 into this thing. So let's see. 1 over 0 plus 1. That's plugging in to this expression here. Times 1 minus 0 over 3 times 1. So when I plugged it all in, the answer is 1/3. And if you got 1/3, you should pat yourself on the back, but not too hard, because that's not the final answer. The final answer is e to the 1/3, or the cubed root of e. And let's finish this out. So the limit as x approaches 0 from the right of y equals the limit. Oh, isn't this annoying to write this every time? Sorry, you gotta do it. E to the natural log of y, which equals the limit as x approaches 0 from the right. Goodness gracious, I did that again. Which is e to the limit as x goes to 0 from the right of natural log y, which is e to the 1/3. That is my answer, or I can write it as cubed root of e. And what I just drew here was a smiley face. I would like to briefly discuss an application. The formula written here is talking about maybe perhaps money growing. The amount you have in a bank is the principal times 1 plus r is the rate at which it grows. N is the number of compounds. Maybe it's compounding monthly, so n would be 12 to the n times t is the number of years. And if I took a limit, let's say the limit as n goes to infinity of 1 plus r over n to the n, then that's like saying money, instead of compounding every month or every day or every second, is compounding every minute of every second of every day. It's compounding continuously. So if you work out this limit, it shouldn't surprise you that this will come out to be e to the r. So if I take this growth model and it's p, and instead of writing this, I wrote e to the r to the t, then that comes out to be what a lot of people recognize as PERT, principal times e to the rt, which is simply the same as here, except that it's compounded continuously. Now, what in life is compounded continuously? Well, we are. Biology. Things grow every minute of every second of every day. Imagine we didn't grow continuously. At the end of the year, boom, suddenly we're 6 inches taller or 5 inches taller, etc. So E is nature's natural base, and hence the name natural log, resulting from nature's natural base. See ya.